So because I teach meteorology and climate, I have a different view of the atmosphere of the Earth and the text reference to the greenhouse effect. And so I wanted to present this lab to you so you can get a better idea about climate change and what some of the misconceptions are about how climate change works, starting with the greenhouse effect. So how is the Earth's atmosphere different from a greenhouse? This is a greenhouse, and the Earth's atmosphere has a much better venting system than this greenhouse, where you see some ventilation from the fans, but you don't see the air moving out. You don't see the air moving in. So the air is moving around with the fans, but you don't see a lot of air movement in to out and out to in. So, and on top of that, the Earth plus the Earth's atmosphere together are a better black body than this greenhouse. Remember, a black body emits all radiation that it absorbs. Remember, the black roadway absorbs all the radiation during the day, emits during the day because everything emits at all times, and emits all night. And by being such a good black body, that asphalt roadway at dawn is cooler than the dirt next to it. In talking about that, when you link the Earth with the Earth's atmosphere, it makes for a very good black body. Not a perfect black body, a very good black body, and a better black body than that greenhouse that I showed you before. An Earth with an atmosphere and no greenhouse gases in the atmosphere is a nearly perfect black body. And this is a representation of the Earth with an atmosphere and no greenhouse gases in that atmosphere. In that case, the energy coming in from the sun, everything would be absorbed by the Earth, and it would all be emitted by the Earth all day and all night. But if we had the Earth with an atmosphere and no greenhouse gases, we wouldn't be talking right now. We wouldn't be living right now. There would be no way to maintain all three phases of water, and those phases are all critical to life: ice phase, water phase, and water vapor phase. You would simply have ice without the greenhouse gases, and ice alone is not conducive to life. You need at least the liquid phase to be conducive to life. That's what we know, and that's what we look at on other planets in our solar system. We look for water. We look for water that is not ice, because we couldn't survive on this planet without the greenhouse gases that make our environment warmer. So let's talk a little bit more about what the greenhouse gases do for us. Our atmosphere does have greenhouse gases. They absorb and emit light wavelengths very selectively, and these greenhouse gases are not perfect black bodies. They do not absorb all the wavelengths that are coming at them. They absorb very selectively. They do not emit all the wavelengths that they did absorb. They emit very selectively. I'm going to talk about that a little bit more. The greenhouse gases that we're concentrating on are CO2, CH4, which is methane, and N2O, which is nitrous oxide. We're also going to talk about ozone as well. When we put together our atmosphere with greenhouse gases and the Earth, we become a very comfortable black body. So the Earth is a very good black body. The atmosphere, not such a good black body. When you put the two of them together, they're a very comfortable black body. And they're much better than that greenhouse that you saw at the start. And part of this is that the Earth and its atmosphere are really responding to the second law of thermodynamics on a very large scale, that all systems, the universe, any substance, even that greenhouse, tends to move toward an equilibrium, like you know, and this is a radiative equilibrium, meaning that all substances want to absorb as much radiation as they can and emit as much radiation as they can. The greenhouse is just having a harder time doing it because the landscaper put a lot of insulation in the way to prevent the emissions. Now, when it comes to the sun emitting, the sun, as you know, mostly emits in the visible wavelengths of light. And beautifully, the Earth absorbs mostly invisible light. Our atmosphere does not absorb the visible light. Our Earth absorbs the visible light. And as a result, we see all these beautiful colors through our eyes, which are actually spectroscopy devices. Now, everything that is absorbed by the Earth, if it's a black body, tends to be emitted by the Earth. And the Earth will emit at its temperature so that while it absorbs high energy visible waves, it doesn't get that warm to emit high energy visible waves. Instead, the Earth emits lower energy infrared waves. That's what you're seeing here on emissions. This is an emission chart here. These are the Earth's emissions, lower energy IR waves. These are the sun's emissions, the high energy visible waves, which we view through our little spectroscopic devices in our eyes. When it comes to the waves that are coming into our Earth, like we said, absorbs, and absorption here is in black. Our Earth absorbs in the visible range. What we're looking for here is we're looking at absorption by the atmosphere around Earth, not by the Earth itself. So this graph is a percentage of absorption by the atmosphere. And you see a lot of black here. And this, of course, is the UV range. And there's an enormous amount of absorption by the atmosphere in the UV range. That absorption is in the stratosphere about 12 miles up, and it's done by ozone in the ozone layer. Ozone is a greenhouse gas. We could not survive on Earth without ozone. And when there was an ozone hole, particularly at the Antarctic, people were very concerned about skin cancer rates during that time. Ozone as a greenhouse gas is completely critical to our survival on Earth. It absorbs the UV here. Now, in terms of all of this absorption and all of these black, I don't know, what would you call them, peaks there? All of these black peaks are also caused by greenhouse gases. That absorption and those greenhouse gases are completed by carbon dioxide and water vapor gas. That is absorbing in the near IR range, near infrared range, and absorbing in the infrared range, which is here, and through here. This is all IR with the tan background. So carbon dioxide and water vapor together are doing an enormous amount of absorption of IR. Now you may say, I thought the Earth emitted in IR. Let's talk about that a bit more. The Earth does emit in IR. There is a well here where there is a well here where there is quite a drop in absorption in black. That well that you see, which is between 8 nanometers and about 11 nanometers, is in white. Now you say, excuse me, but there's a very large peak in there, right around 9. The large peak is relative. The large peak can be accomplished from free ozone in the stratosphere, but free ozone in the stratosphere is rare. Most of the ozone in the stratosphere is preferentially selecting for the UV. So we have what's called an atmospheric window where the Earth can emit IR spectra between 8 nanometers and 11 nanometers directly to space. And in that area is how the Earth balances out the absorbed energy coming in and all of the emitted energy which needs to go out. It goes out through that atmospheric IR window in white. Specifically, let's look at what carbon dioxide and water vapor do for us. Let's take apart this into their individual contributions. When we look at carbon dioxide does absorb in the near infrared range, and it absorbs selectively in the infrared range. There is some absorption peak here, right around 4 nanometers, and there's a broader range of absorption from about 12 nanometers to about 20 nanometers for carbon dioxide. When that happens, when the CO2 in the atmosphere absorbs the emissions from the Earth's surface, guess what? It has to emit as well, because everything that absorbs has to emit. So the CO2 in the atmosphere that has absorbed this IR now has to emit it right back down to the Earth's surface again. Does it sound like a ping pong? Yes, it does. It gets absorbed, it gets emitted. It gets absorbed, it gets emitted. And it bounces around like a ping pong, which is what we're talking about with the amount of CO2 in the atmosphere. As it increases, there's more ping ponging. There's more of a temperature rise. But let's look at water vapor. Water vapor is the culprit that nobody talks about. Water vapor absorbs far more in near infrared, and water vapor absorbs far more in infrared than carbon dioxide. When we talk about the storms that are coming through this summer with the hurricanes and into the fall, we're talking about the energy that is in all of this water vapor, which is evaporating off of the oceans. When we talk about climate change, we're talking about increased water evaporation and the ability to hold all of this energy and ping pong it up and down from the surface. We can't control water vapor in our atmosphere nearly as effectively as we can control carbon dioxide. So we talk about carbon dioxide and global climate change because we really can't control water vapor nearly as effectively. When it comes to this is a reflection of Earth's energy coming in and Earth's energy being emitted out. When it comes to the greenhouse gases, you see it being emitted and absorbed and then coming right back down to the surface. It's different here. Talk to you soon.